EDX Core Pure, Matrices 2, Transformations and Invariants. Transformations in 3D. The following simple transformations in 3D will be covered. So we'll have reflections in one of the following planes. So we can have z equals 0. If z equals 0, we are looking at the usual two-dimensional xy plane that we're familiar with. If y equals 0, then we're looking at the xz plane. If x equals 0, we must be dealing with the yz plane. Rotations of 90 degrees or multiples of 90 degrees about one of the axes will also be covered. Be careful when doing rotations. The positive direction of a 3D rotation is counterclockwise when looking towards the origin from the positive side of the axis of rotation. The simplest way of looking at this is if you think about the usual XY plane that we have been rotating in previously. If you're looking towards the XY plane from the positive Z axis, you would be dealing with an anti-clockwise rotation as being a positive rotation. So when we're looking for a 3D matrix, it is very similar to when working with a 2D matrix. If we work out what happens to the one unit along the x-axis, so that's 1, 0, 0, and 1, 0 along the y-axis, so that's 0, 1, 0, and 1 unit along the z-axis, 0, 0, 1, then each of the images of those 3 points will be the corresponding columns of the matrix. So the first column of your matrix will tell you what happens to 1, 0, 0. The second column of your matrix will give you the image of 0, 1, 0. And the third column of your matrix will be the image of 0, 0, 1. So if we look at this little example, here's our three-dimensional matrix M. If we start looking at the Z column perhaps, so this column here is telling me the image. So this is the image of one unit along the z-axis, and you can see that it is exactly the same. This column here is the image of one unit along the y-axis, 0, 1, 0, and it's exactly the same. It's the first column that's the interesting one. So the first column represents the image of one unit along the x-axis. So that's the image of 1, 0, 0, 1. So the image of 1, 0, 0, 1 is minus 1, 0, 0. The y-coordinate's the same. The z-coordinate's the same. So this matrix represents a reflection in the YZ plane. The y and z coordinates have remained the same, but the x coordinate has been reversed. So it's a reflection in the YZ plane or the plane x equals 0 if preferred. If we look at this new matrix M, and again if we do them one column at a time, so the third column is the image of 0, 0, 1. So that is exactly the same. The second column is the image of one unit in the y direction. So that one has been reversed. And the first column is the image of one unit in the x direction, and that one has also been reversed. So our z coordinate is exactly the same. Our y coordinate has changed sign. Our x coordinate has changed sign. And the only way that can happen is if we've got a 180-degree rotation about the z axis. So if you look at this illustration, the z coordinates have all remained the same, but the positive x coordinates have become negative x coordinates, and the positive y coordinates have become negative y coordinates, and we've got our 180-degree rotation about the z-axis. There will be some integral notes for you to have a look at, talking about three-dimensional transformation matrices, and you can try investigating this in the 3D view on GeoGebra, and there's help on that on the web page provided. In the next session, we're going to be looking at invariant lines and points.